Thorium. Behind this name, which echoes the famous Scandinavian god, hides a mysterious chemical element. Discovered in 1829 by the Swedish chemist Jöns Jacob Berzelius, this new metal found its practical use in Europe in incandescent mantles about 50 years later. Indeed, less bright and heating more, the old flame lamps were gradually replaced by these. Thorium-based mantles will be prized for their stability and their white light until the middle of the 20th century. Today, thorium is used in the industry, for example, to make optical lenses. In marine science, it is used as a chronometer to calculate the velocity at which solid particles fall from the surface to the bottom, and thus provide researchers with essential data for climate models. Let's take a closer look. Thorium atoms are insoluble and stick to particles. Moreover, they are radioactive. This means that they are unstable, and that each of its atom variants, called isotopes, decays at its own pace, or rate, after which they transform into a new chemical element. This is naturally occurring. This pace of decay works like a natural chronometer. At the ocean surface, biological activity generates a rapid flow of particles. Scientists then use a rapidly decaying isotope, Thorium-234, which is a chronometer adapted to this rapid pace. It tells us at which rate solid matter is exported to the deep sea. At depth, everything is slower. The researchers will therefore use the slowly decaying Thorium-230 as a chronometer to tell us how quickly solid matter settles to the sea floor. Researchers were therefore able to establish that the sinking velocity of the material was 800 meters per year on average, but that it could reach 1,000 meters per day in some places. This result is extraordinary because no one can dive with a chronometer to a depth of 3 kilometers to make this measurement. However, you might wonder what the link is between thorium, carbon, and climate models. It is this velocity measured, thanks to thorium, that allows researchers to assess the rate at which carbon is sequestered at the bottom of the sea, which is important information for climate models. Now, let's look at this in more detail. The deep ocean holds vast amounts of carbon sequestered by a biological process taking place in the ocean's surface where CO2 dissolves from the atmosphere. It is assimilated by the algae, which use the sun's light energy and this carbon to grow. When these algae die, this solid organic carbon falls by gravity to the abyss. It passes through the first 200 meters, timed by the Thorium-234. Then, it is sequestered at depth, timed by the Thorium-230. So if we review, CO2 is transformed by the phytoplankton into solid organic carbon. As it falls towards the seafloor, its pace is timed by Thorium-234 for the first 200 meters. Then, the pace at which it is sequestered at depth is timed by Thorium-230. Without thorium and its isotopes, the sequestration rate of carbon by marine life could not be integrated into climate models. Because thorium can provide important chronometers, it is easy to understand why it's such a major parameter in the GeoTraces international program.